let's say I've got, sure, I've got this. So I've got dx1 dt, and I'm going to make up some numbers that might turn out terrible. We're going to find out. dx1 dt is equal to negative 4x1 plus 0.6 x2, and dx2 dt is equal to, let's say, thank you, 3x1 minus 0.8 x2. And I'm going to draw the standard compartment model for this sort of situation. So when someone says compartment model, you should think of the following diagram. He says he's probably about to draw it wrong. So you've got x1 and x2. And it doesn't really matter what labels you use. I say that because I'm about to probably use non-standard ones. I'm trying to zoom around it. We've got stuff going out of x1 into x2, stuff going out of x2 into x1, and then we typically have stuff going out of x1 and out of x2. That's the usual kind of picture we draw. And I forget which letters go with which, to be honest. I feel like, I mean, it doesn't really matter.
I remember it's A, B, C.
A, B, C, D. Great. So what we're saying here is, well, I would say it's A times x1, it's B times x2, it's C times x1, and it's D times x2. The picture is the easiest way to, sorry, can you guys see that all right? My writing feels especially light today. So this is our picture. And the equations we are going to have are really just what's going in and out of x1. So the rate of change of x1 is, okay, I'm losing cx1, I'm losing ax1, I'm gaining bx2. So it's minus ax1 minus cx1 plus bx2. And then the change of stuff that's going in and out of x2, I'm gaining ax1 and I'm losing bx2 and dx2. And then we typically, like I've written this kind of the long way, you probably want to actually write this as like negative a minus c times x1 plus b times x2. And a times x1 plus negative b minus d times x2. Like, is that all easier? Is that better? That people are kind of like having a hard time seeing what's on there. I think that's a little better. All right. After this, we're really just going to set. We're going to just equate these. So this coefficient of x1 is going to be negative 4. And this coefficient of b is going to be 0.6. So this coefficient b of x2 is going to be 0.6. And this coefficient of x1 is going to be 3. And this coefficient of x2 is going to be negative 0.8. And then we solve for a, b, c, and d. So let's do it. And really, to be perfectly honest, there's not a whole lot of point to solving for a, b, c, and d other than to set up the compartment diagram. Right? We've set it up, and now we're just trying to fill in what a, b, c, and d are. But as far as analyzing the stability of the equilibrium, you don't need to know what a, b, c, and d are at all. You just need to know what you've already got right here. Now, I should point out, if they give you this compartment model and you want to work backwards to finding the stuff, then you do need to kind of know how these equations work, which we can, I guess we can do an example of that as well if you guys want. So I'm going to, well, I've got b and a real easily. A equals 3, b equals 0.6. Negative a minus c equals negative 4, but a is 3. So negative 3 minus c equals negative 4. So negative c equals negative 1. So c equals 1. And negative b minus d equals negative 0.8. But b is 0.6. So negative 0.6 minus d is negative 0.8. So negative d equals negative 0.2. So d is 0.2. So finding A, B, C, and D is pretty straightforward. You're literally just taking, let me back up a little bit here. You're literally just taking the differential equations they've given you and solving for the coefficients. And this is always kind of the standard model that we're going to have. So there's not a lot more to it to solve for those coefficients. If I wanted to analyze the stability of this system, usual thing, find the eigenvalues. Now, I don't love the fact that I've got decimals here, meaning I don't really want to do that work. So I'm going to just remind you all that you could find, thank you. So, right, so our matrix is going to look like, sorry, I'm way out of here, apologies. So if we're analyzing stability, our matrix is going to be -4, 0.6, 3, -0.8. Could I find the eigenvalues actually? Probably. Probably, definitely. We could definitely find the eigenvalues. So if we want to do it the long way, here's how we would do it. Man, okay. -4 minus lambda, 0.6, 3, -0.8 minus lambda. Take the determinant of that and set it equal to 0. I'm not thrilled. I mean, I know we could solve this. I don't want to. I don't want you to have to solve this on a midterm, because although you can, it's kind of a giant pain, right? I mean, let me go one more step and then I'm going to stop. So I'm going to get lambda squared. I'm going to get a plus 0.8 lambda, a plus 4 lambda. So I'm going to have a plus 4.8 lambda. And then I'm going to have a, 4 times 0.8 is 3.2. Plus 3.2 minus 3 times 0.6 is 1.8 equals 0. So I've got lambda squared plus 4.8, and then 3.2 minus 1.8 is minus 1.4. That definitely doesn't factor in any nice way, right? I mean, it's got decimals. I guess you could multiply the whole thing by 10 if you really wanted to give factoring it a shot. But here's what I'm trying to get at. Okay, you could, I suppose I can go one step further. We should use the quadratic formula because it's really the same trace determinant or this. So if I use the quadratic formula, I'm going to get negative 4.8 plus or minus the square root of 4.8 squared minus 4 times 1 times negative 1.4 all over 2 times 1. All right. So we have to decide. I don't want to do any more work here. I want, and we don't have to, the better point. Are my eigenvalues real or complex? Well, look at the square root. Is the stuff inside there positive or negative? Well, I've got something, sorry, I should make the people, I've got something squared, and am I adding or subtracting? I'm definitely adding something because it's -4 times 1 times negative 1.4. So this is definitely positive. So we know we've got real eigenvalues. All right, so then there's 3 possibilities. They're both positive, they're both negative, or one of each. Well, they're definitely not both positive because you got a negative 4.8 out here. So they're either positive and negative or both negative. So here's the thing. This square root got bigger than 4.8 squared. I've got 4.8 squared plus some stuff. So let's call it, let's just pretend for a minute it's 25. I know that's bigger than 4.8. 4.8 squared is less than 25. So let's pretend this is 25 and the square root of it's 5. Negative 4.8 minus 5 is negative. Negative 4.8 plus 5 is positive. And when you're adding stuff on with this part here, you're going to be bigger enough that one way is going to make it positive and one way is going to make it negative. Or, well, I'm going to go back in time in a minute here and show you how we could have done this one with way less work. So they're real and opposite signs. So we know that we have a what? Yeah, saddle time. Saddle in. Now, we could have done this much more easily with the trace determinant method, thinking about the graph that shows you like the determinant on the y-axis and the trace on the x-axis. And down below the x-axis is saddle land. Here's the trace. Here's the determinant. Down here is saddle land. On the right, above the trace axis, over here is unstable land. Over here is stable land. And then specifically above this parabola is spiral land. So on the right side are unstable spirals, on the left side are stable spirals. And down here are nodes. So over here is an unstable node, over here is a stable node. And then this curve here is the curve where, sorry, I have to remember what it is. It's delta equal to 1/4 the trace squared. So if your determinant is bigger than 1/4 of the trace squared, you're in spiral land. If your determinant is less than 1/4 of the trace squared, you're in node land. But if your determinant's negative, you're in saddle land. And the determinant is negative here. The determinant of this matrix is -4 times -0.8 minus 0.6. I said it was negative, and now I'm like totally not convinced it's negative. I feel like I'm a big liar. But it should be negative, right? I mean, no ifs, ands, or buts about it. We already saw it was a saddle. The determinant should be negative. So what kind of, well, let's find out. What kind of mistake am I making here? -4 times -0.8, and then minus 0.6 times 3. That should be 3.2. That should be 1.8. So this is a good thing we did because I made a mistake. It happens. It's all right. That's 1.4. I made a mistake right here. You guys see that? That should have been a plus. So what's the lesson do you mind explaining? Yeah, I'll come back to the compartment. So I guess the takeaway here is to be careful with your work. Right, like what else can I say? So we're actually going to add here. Well, great. So, all right. So it's not a saddle actually. Well, actually, that's not too terrible. We know it's not a saddle. So now we're in the situation where we don't actually know it's real. It could be real. We have to determine, okay, what do you guys think? Is 4.8 squared minus 4 times 1.4. Positive or negative? What's bigger? 4.8 squared, 4.8 times 4.8, or 4 times 1.4? Well, definitely 4.8 squared, right? Both of the factors are bigger. Okay, so this is still positive. It means we still are real, but we know it's not a saddle because the insides here actually got smaller than 4.8. Right? 4.8 squared minus some stuff is going to be less than 4.8 when you take the square root of it. So you've got -4.8 plus or minus something that's smaller than 4.8, meaning -4.8 minus it is negative, and -4.8 plus it is still negative, meaning they are not opposite signs. They're actually real and both negative. Sorry, so I will remind you all, hopefully the numbers are not quite as not nice as this if you have a question like this in your test, but just to be extra careful when you're finding the actual values of the eigenvalues. This is kind of a not lovely example, but it's not totally ridiculous. Let's look at one more example. I should back up actually. Questions before we move on to another example. So get asked questions. How do we find T? Oh, sure. So I assume when you say T, you mean the trace. So in this matrix, the trace is -4 plus -0.8. It's the sum of the diagonal elements, which is -4.8. And the determinant is what we found correctly the second time around, 1.4. And I will point out that we're not in saddle land because the determinant's, whoops, we're not in saddle land because the determinant's positive. So we're somewhere up here, but we're definitely in stable land because our trace is negative. And so we only have to determine, are we a node or are we a spiral? Meaning are eigenvalues real or complex? And that totally depends on if your tau squared minus 4 delta is positive or negative. And in this case, it is positive, right? We just literally calculated, right? That's the 4.8 squared minus 4 times 1.4. So, sorry. What I'm trying to say is that you can see what your solutions look like, or I should say, you can classify your equilibria just by looking at the trace and determinants. You don't have to actually find the eigenvalues, although a lot of the time it will be easy to find them, but you just should because it's pretty easy once you find them. But if you feel like the eigenvalues are starting to look super ugly, you can just be like, oh, trace, determinant. If the trace is positive, unstable. Trace is negative, stable. Determinant's negative, saddle. Determinant's positive, okay, then you have to do a little bit more work and see if they would have been complex or real. Let's start aside, yeah.
So you're determining the equilibrium act. So you find trace and then using that formula, do you have to square the trace in order to?
Yeah. So I'm gonna show you, I'm gonna draw it again just so you can kind of see it better. So on the y-axis is my determinant. Up here, determinant's positive. Down here, determinant's negative. Over here, trace is negative. Over here, trace is positive. Sorry. And then if your determinant's negative, we have a saddle. Because if the determinant's negative, your eigenvalues are opposite signs. But they have to be.
But then after you multiply it by 4, right?
Well, so there's kind of two different things here. So I'm really just looking at the determinant right now. So if the determinant's negative, saddle. That should be kind of, if you're doing this trace determinant method, that should be the first thing you look at. Is the determinant negative? Yes, saddle. No, do more work. So if it's no, then you have to ask yourself, okay, well, what's the trace doing? So over here on the left side where the trace is negative, we have stability. Over here where the trace is positive, we have instability. And I feel like I should have written it on top because that's kind of more where it actually is, right? Over here, we're looking at the trace being positive. Over here, we're looking at being negative. Over here, we don't care if the trace is positive or negative. So here we have unstable nodes. Here we have unstable spirals. Here we have stable nodes. Here we have stable spirals. And the determining factor between node and spiral is, for the nodes, we need the trace squared minus 4 times the determinant to be positive, aka the discriminant in your quadratic formula is positive. And for unstable or stable spirals, the discriminant has to be negative. And this is the parabola that kind of decides that. So if you're trying to use the trace determinant method, look at the determinant. Negative, saddle. If it's positive, then you ask yourself, okay, is my trace positive unstable. Is my trace negative? Stable. Right, because it's not a saddle anymore, so it's not like one or the other. So if your trace is negative, it's either a stable node or a stable spiral. If your trace is positive, it's either an unstable node or an unstable spiral. And then you have to determine if it's a spiral or a node by determining if your eigenvalues are complex or real. Complex if the discriminant's negative, real if the discriminant's positive. Is this the best way to do it? Not all the time, right? A lot of the time it's going to be like, if you feel like your quadratic formula is super easy to just factor, do that. But if you've got something gnarly like what I made up here, I think this is kind of a better way of doing it. What I should really say is you should do whatever you're most comfortable with. If you are capable of dealing with these situations in whatever way works well for you, do it that way. I think this is nice. Some of the time, I also think factoring is good some of the time. Yeah.
What does the parabola represent?
The parabola is the line where, or the curve where we change from stability to instability. So this parabola is the equation tau squared minus 4 delta equal to 0. Although in the textbook, they prefer to write it as, they like to solve for delta, and they say that delta equals 1/4 tau squared. It's the same thing. And on this parabola here, you have, actually, I feel like on the parabola, they don't actually talk about what that means. On the parabola is kind of like funky, but on this line right here, where the trace is equal to 0, you have a neutral spiral. Okay, if you have a 0 trace, if your eigenvalues are purely imaginary, you don't have a spiral inward or a spiral outward, you have a spiral that just keeps looping around and around and around in the same spiral. So for question, so yeah, so let's talk about the one more example of the compartment model, and then we'll move on to some other stuff. So let's say we were given the diagram this time. Let's say we have 2 compartments. X1 and X2. And I'm going to try and make things come out slightly nicer than we did last time. So let's say X1 is going over here with a 1.2, X1 going out with a 0.8. This way with a 3, X2, going out that way with a. To be perfectly honest, I have no idea if this is going to turn out well. Okay, it'll turn out somehow. So let's write down the differential equations. Let me ask you all, what's leaving X1? Well, I'm losing 1.2 X1, I'm losing 0.x1. So I'm losing a total of 2x1. I'm gaining 3x2. Okay, let's look at x2. So for x2, I really am looking at like what's happening with x1. So into x2, I have 1.2 times x1. And then what's happening to x2, I'm losing 3x2 and 2x2, so I'm losing a 5x2. So there's my compartment model. So why is it over dt? Because typically we're thinking about how the amount of stuff in the compartment is changing as time goes on. Almost all the time when we talk about rates of change, we're talking about how things are changing as time is changing. It's not like 100% of the time, but it's almost all the time dt. So now we don't need to find A, B, C, and D. They gave it to us already, right? There's A, there's B, there's C, there's D. We could have actually, you could memorize those equations. I honestly couldn't. I mean, okay, it's like negative A minus C x1 plus bx, right? Don't memorize those. Memorize how to get from the picture to the thing, or to the thing, from the thing to the picture. Or don't memorize, but like see, right? I'm not memorizing this. I'm just like, oh yeah, Got my picture. I'm like, what goes into X1? Well, what goes out of X1? I'm losing that. I'm losing that. What goes into X1? I'm gaining that. What goes out of X2? I'm losing that. I'm losing that. What goes in? I'm gaining that. That's how I'm getting these things here. How is it negative 2x1? Because that's a good question. It's a minus 0.8x1 minus a 1.2x1. And the same deal for the 5x2 or the minus 5x2. It's a minus 3x2 minus 2x2. Let's analyze the stability. All right, I'm going to try and do it just using trace determinant. So let's find the determinant first. I suppose I could write the matrix first. Negative 2, 3, 1.2, negative 5. Determinant's going to be 10 minus 3 times 1.2, which is 6.4. It's positive. We have to do more work. So it's not a saddle. Let's find the trace. Trace is going to be negative 2 minus plus negative 5, negative 7. So great, we know we have stability. The only thing left to see is it a stable saddle? Which is not a thing. Sorry, words. Sometimes the words come out wrong in my mouth. I apologize. Is it a stable node or a stable spiral? Not saddle. So that question we're asking is just, what's the deal with the discriminant? What is the trace squared minus 4 times the determinant? All right, well, I don't actually have to calculate it. I just have to know whether it's positive or negative. So the trace is negative 7. And the determinant is 6.4. All right, is this quantity positive or negative? Definitely positive, right? That's 49. There's no way that's 49. It's 24-ish, 25-ish, certainly not any bigger than 30. It's definitely positive. Okay, now what does that mean that it's positive? What would our eigenvalues be? Real or complex? Real, right? Because the discriminant is not negative. We're not taking the square root of a negative. So that means, oh, we have a node. So we have a stable node. Or you could find the eigenvalues in a different way. You'll probably still end up having to use the quadratic formula here, though, because again, this decimal is making things less than nice. And it's pretty common to have decimals pop up when you're seeing a compartment model. It's the way it goes often. Okay. Let's talk about nonlinear systems and differential equations. So imagine that is the thing that is on most of your minds. Let me leave this up here for a sec, sorry. Sit down. So let's look at this nonlinear system. Let's say we've got dx1 dt. Yes, with respect to t, right? We're asking how x1 is changing as time is changing. It's going to be 3x1 minus x1 squared minus x2. And dx2 dt is x1 minus x2. And I'll just point out that, I mean, he'll probably tell you it's nonlinear, to be honest. But you're going to be able to tell it's nonlinear if it looks different, right? If it looks any different than constant times x1 plus constant times x2 for both equations, right? That's what the linear ones look like. It's some ax1 plus bx2, and then the second one is some cx1 plus dx2. We don't have that here, right? We've got a more complex, not complex, but like a more complicated situation, a nonlinear situation. We've got something squared. So how do we deal with this? Well, there's a couple ways. My words of advice are to take the path of least resistance, meaning try to figure out what x1 or x2 is in the easier looking one. Which one looks easier? The second one. Right? I should say, I'm going to set each of these equal to 0 because we're trying to find the equilibria, right? Where the rate of change is 0. There was a question about, oh, yeah, someone asked and someone answered. Yes, so in the previous one, it's stable because the trace is negative. If the trace, right, not bigger than 0, the trace is less than 0 in this one. That's why it's stable, because your eigenvalues are going to be negative because the trace is negative. So I'm going to say, all right, well, x1 equals x2. That has to be true. So whatever equilibria I find, the x1 and the x2 coordinate are going to be the same. I don't have a choice. But now I'm going to use that and I'm going to sub it into the other equation. So I'm going to write this as 3x1 minus x1 squared minus x1 equal to 0. So I'm going to get 2x1 minus x1 squared equal to 0. So I'm going to have x1 times 2 minus x1 equal to 0. So I'm either going to get x1 equal to 0 or x1 equal to 2. Pairing that with the fact that this also has to be 0 means that my two equilibria are 0, 0, and 2, 2. Those are my equilibria. All right. To classify the equilibria, we need to do the same sort of thing we've been doing, but we have to get the matrix first. So in the past, I mean, we've actually been doing this already, but we just haven't been talking about it. So when you find the matrix, like for example, if your equation is something like dx dt equals 3x plus 4y, dy dt equals 2x minus y, and the matrix is 3, 4, 2, negative 1. That is the Jacobian matrix of these equations, right? Where you're finding the partial of the first equation with respect to x, which is 3, the partial derivative of the first equation with respect to y, which is 4, the partial of the second with respect to x, which is 2, the partial of the second with respect to y, which is negative 1. So you're already finding those partials to find this matrix. We just never talk about it that way because it's like, oh, it's just the coefficients because it's all linear. But now we're going to do that for this. So typically, people like to call this first one f and the second one g, or if you prefer, f of x1 comma x2, g of x1 comma x2. You don't have to call it that. Our Jacobian is, so here's what I remember it. Top function in the top, bottom function in the bottom. First variable in the first column, second variable in the second column. So in the top, it's going to be f, in the bottom it's going to be g, in the first column it's going to be x1, in the second column it's going to be x2. So I'm going to take my partial of f with respect to x1, my partial of f with respect to x2, my partial of g with respect to x1, my partial of g with respect to x2. To me, that's the easiest way to remember it. So that's going to be, so fx1 is going to be 3 minus 2x1. fx2 is going to be negative 1. gx1 is going to be 1. gx2 is going to be negative 1. Here's my Jacobian. And then we evaluate our Jacobian at the various equilibria we have to see, and then to analyze the stability. So if I'm going to evaluate my Jacobian at the point 0, 0, I'm just plugging in 0 for x1 and 0 for x2. There is nowhere to plug in 0 for x2. If I plug in 0 for x1, I'm going to get 3, negative 1, 1, negative 1. And since I want to make life easy, well, I made life easy. The determinant is negative 3 minus negative 1, which is negative 2. Oh, we have a saddle. You could also find the eigenvalues. I don't really want to, though. But I will if you guys want to. Let's look at the other one, though, and then we can come back and talk about that if we need to. If I plug in 2, 2 instead, I get 3 minus 4, so -1, -1, -1, -1. And so then I don't think it's going to be a saddle, so I should probably actually do the work. My trace is -2. My determinant is 1 minus -1, which is 2. And although I've been talking about doing it the way I've been doing it, it also is relatively not terrible just to write out the quadratic formula at this point and say, okay, my eigenvalues are my trace plus or minus the square root of my trace squared minus 4 times my determinant all over 2. And it looks like my eigenvalues here are going to be complex because my inside of my square root, my discriminant is negative. So we're complex. I mean, aren't we all? And stable or not? Stable, because our real part is negative. When you think about being stable or not, it's always about the trace. So if the trace is negative, so I should say, assuming we don't have a saddle, if the trace is negative, you have stability. If the trace is positive, you have instability. If the determinant's negative, then whoops. How about instability right there? The traces or the determinant's negative, you have a saddle. If the determinant's positive, which it is, then okay, this determines your stability. So we have a stable spiral. The quadratic formula is negative b plus or minus square root of b squared minus 4ac over 2, but you have it as b. Well, so here's the thing. That's an excellent observation. But here's the idea. Here's where this is actually coming from. So if you actually write out, in fact, I'll just tell you. So when you find, like when you take the determinant of a minus lambda I, here's what you actually get. You get lambda squared minus the trace times lambda plus the determinant. That is, at least for a 2x2 matrix, every single time. This is called the characteristic polynomial. That's what this is always actually equal to. So if you're trying to solve this equal to 0, your A value is 1, your B value is negative the trace, and your C value is the determinant. So when you throw it into the quadratic formula, you get negative tau plus or minus the square root of negative tau squared minus 4 times A times C all over 2. But we usually simplify this as the trace plus or minus the square root of a negative thing squared is the same as the positive thing squared. That's why we get to write it like that. So 2 questions I see. First question, what does complex mean? Complex just means that our eigenvalues have an imaginary part, or we're taking the square root of a negative, right? So if we're complex, we're taking the square root of a negative. If we're real, we are not taking the square root of a negative. And then why is the spiral stable? Well, because if we look back at our answer, I know I didn't finish it because, again, I'm trying to be efficient with the time when I'm taking this test. Right? If I look at this, I can say, okay, well, if I actually finish this off, my eigenvalue is there. And again, this is for the point 2, 2. My eigenvalues are -2 plus or minus the square root of, okay, 4 minus 8 is -4. And then I get -2 plus or minus the square root of -4 is 2i. And then that's going to be -1 plus or minus I. Our eigenvalues are imaginary, so we know we have a spiral. And the real part is negative. That means we are stable. Oh, sorry. Yeah, thanks. So real part being negative means we're stable. Complex means we have a spiral. And again, I want to mention, I don't think you need to actually get all the way to what the eigenvalues are if they haven't asked you to find it. So I want to be extra clear about that. Right? You might need to find the eigenvalues if you're trying to find the general solution or the particular solution, right? And not just might, you definitely will need to find the eigenvalues if you're finding the general or particular solution. But if they're just asking you to classify an equilibria, you don't actually even have to find the eigenvalues. You just have to know what they look like. I mean, you have to know if they're real or complex, and you know if they're positive or negative, or one of each if they're real, or have a positive or negative real part if they're complex. That's all you have to know about the eigenvalues. But you don't ever need to actually know their values if you're just asked to classify the stability. Can you know them? Sure. Should you find them if it's easy? Yeah. It's probably easier to actually find them some of the time. But if your thing looks gnarly, you might want to do it a different way. And again, I'll say one more time, you should do it the way that you do it the best. Right? If you're like, I don't love this trace determinant garbage James is talking about all day and all night, I can just find the eigenvalues using the quadratic formula every single time, or factoring if it looks like it factors, then do that. But sometimes you're right. If you have eigenvalues, well, no, that's not true. Take that back. Do that. Let's look at another example. Let's look at this system of non-linear equations. We have dx1 dt equal to 10x1 minus x1 squared minus 2x1 x2, and dx2 dt equal to 10x2 minus 2x1 x2 minus x2 squared. Looks kind of gross. I feel like before we get too into this one, I should back up for just a second because I missed an opportunity to say something about the null clines. I know you guys were asking about the null clines. So let's back up for just 1 sec. We'll definitely come back to this one. But I do want to, if we look back at the previous problem, look back at this one for a second, we had a couple null clines. We have this null cline, x1 equal to x2, or if you might want to think about it for graphing purposes, y equal to x. And then we also have, we have a couple null clines here. We have x equal to 0, or we have, I'm getting a little ahead of myself there. That's not quite exactly right. So this one's, if I thought missing opportunity, no, you can totally find this one. Okay, fine. So the null clines are where each equation is separately equal to 0. So if we're going to think about this one being 0, I'm going to isolate the quote unquote y thing. And the null cline here is going to be y equal to 3x minus x squared. So those are my null clines. They're the lines or curves where one of the derivatives is always equal to 0. So here's what this means if you're trying to like draw the direction field or the phase plane for this. Actually, use a different color. Let's do this one in green. Just so we can differentiate. So here's my null cline, y equals x. And on this null cline, what do we know is true? Well, on this null cline, we know that dx2 dt is equal to 0. Or if we're thinking of x2 as y, dy dt is equal to 0. So on this line, there's no change in the y direction, meaning your arrows don't point up or down at all. Your arrows are purely horizontal. So on this line, we're either purely to the right or we're purely to the left. Okay. My other null cline is this parabola, y equal to 3x minus x squared, or y equal to x times 3 minus x. Sure, let's do that. Here's what that looks like. Oops. And on this parabola, there's no change in the x direction, right? dx dt is equal to 0. So all the change is not horizontal, all the change is vertical. There is no change left to right, there's only change up or down. So the arrows would point up or down on this thing here. And where the null lines intersect, I should say, where the null lines of different type intersect. That's where you have equilibria, because where the null lines intersect are where both dx1 dt equals 0 and dx2 dt equals 0. And I don't know how much he has said about null lines in class or what his expectations are around null lines are. But I feel like, you guys, does anyone have anything to say about that?
Talked about it like last class, and then
Mhm.
I asked him, but he said like last class's material won't be on this
Okay.
term, so it'll be on like the final.
Sure. Okay. So we can wait on that to say more about it. But that's very broad stroke, is when you're finding the null lines, the places where the x1 null lines, sorry, the x1 null line and the x2 null line, the places where those intersect is where you have equilibria. This is where you have both derivatives equal to 0 at the same time. We'll talk more about that next week. Okay, let's look at another example. And I think someone had a question over here. So the hashes, so if we were, oh, okay, all right. Yeah, fair enough. We'll save the hashes in a second. So I will just point out that these aren't so much hash marks, is that they're just arrows without the point. I didn't draw the arrowy part because I wasn't sure if they were going up or down. I didn't draw the arrowy part here because I wasn't sure if they were actually going left or right. We could pick a value and plug it in and see, but I think our time is better spent doing other things. So we'll definitely revisit this next week. I know, right? It's like, let's focus on what's going to be on the test. Okay, so let's go back to the, oh, but there was a problem on how the exam word the problem. I think this will confuse me on what to solve for. I'm not, for the person who wrote the question about can we do a problem on how the exam would word the problem, I need a little more clarification on that. So let me, oh, I think I know what you're saying, but if you want to write more in the chat, please feel free. So let me write some words for this as opposed to just writing equations. So what we were going to do here is we're going to find and classify all equilibria for this system of non-linear differential equations. That's probably how something like this would be phrased. No worries at all. Okay, so we're going to set each equation equal to 0. And again, I'm going to encourage you all to look for the things that are easy first. So I have both 10x1 minus x1 squared minus 2x1 times x2 equal to 0. And I also have 10x2 minus 2x1 x2 minus x2 squared equal to 0. And the first thing you should look for is, can you factor any of this stuff? I know I couldn't before. Well, I guess I could before, but yeah. So here, I definitely see I can factor out an x1. I'm left with 10 minus x1 minus 2x2. And here, I can factor out an x2. I'm left with 10 minus 2x1 minus x2. And we're trying to find all the ways, all the points where both of these are 0 at the same point. And there's one really, really obvious answer. What could x1 and x2 both be? 0. And usually 0, 0 is almost always an answer, whether it's linear or nonlinear. So definitely, we could set x1 equal to 0 and x2 equal to 0. And that's one of your 4 equilibria that this problem has. But that's not the only way that both of these equations are 0 at the same time. We could also set x1 equal to 0 and 10 minus 2x1 minus x2 equal to 0. It doesn't have to be true that x2 is 0. If x1 is 0, I could have this part being 0. But if x1 is 0, this part's going to go away. And so I'm going to have 10 minus x2 equal to 0. So I'm going to get x2 equal to 10. Now I want to point out it's not just x2 equal to 10. It's specifically when x1 is 0, x2 is 10. So I get the equilibrium 0, 10. But I could also have the kind of reverse. I could have this one equal to 0 and this one equal to 0, which is going to result in the same sort of thing but flipped. If x2 is 0, then I'm going to get 10 minus x1 equal to 0. So x1 is going to equal 10. So I also have 10, 0. And then finally, the hard part, where both this and this are 0 simultaneously, which wouldn't be true at 0, 0, right? They're both not 0 when x and y. I mean, you still get the whole thing being 0. But specifically, if I want this factor to be 0 and this factor to be 0, I have to do a little bit of algebra. I'm going to solve one of these for one of the variables. Let's go ahead and take this one. Let's say I've got 10 minus 2x1 minus x2 equal to 0. And let's isolate x2. And let's plug that into the other one. So then I'm going to have 10 minus, instead of 2x2, I'm going to have 2 times 10 minus 2x1. That's going in for my x2. And now I can solve this. I've got 10 minus x1 minus 20 plus 4x1 equal to 0. And negative x1 plus 4x1 is 3x1. And 10, I feel like I'm making a small mistake here. No, I guess that's right. Let me double check just to make sure I don't totally. Yeah, that's right. So then 10 minus 20 is minus 10. So I've got 3x1 equal to 10. I've got x1 equal to 10/3. If I plug that back in for x1 here, I'm going to get x2 equal to 10 minus 20/3, which is also 10/3. So my fourth equilibrium is 10/3, 10/3. And if you look back, right, I don't want to look at this version because it's kind of hard. But if I plug in 10/3, 10/3 for x1 and x2, well, look what I get. I get 10/3 times 10 minus 10/3 minus 20/3. But minus 10/3 minus 20/3 is just minus 10, right? It's minus 30/3, which is 10. And I get the same deal here. I get 10 minus 20/3 minus 10/3, which is 10 minus 30/3, which is 0. So setting both x1 and x2 equal to 10/3, this part and this part are both 0, which makes them equal to 0. So when you're solving something like this, you have to find all the points that make both equations 0 at the same time. Kind of funky. All right. And then we have to classify them all. So we can find the Jacobian and plug in each of, right? It's kind of a long problem. Let's do it. So it's nice to find the Jacobian using the unfactored form. I definitely encourage you, if you have something factored, multiply it out before you find the Jacobian. So my Jacobian here is going to be, okay, again, right, we're calling the first one F. We're calling the second one G. So it's going to be, I really think it might be worthwhile to do this when you find it. The derivative f with respect to x1 is going to be, I didn't give myself enough room here, really. It's going to be 10 minus 2x1 minus 2x2. The derivative f with respect to x2 is going to be 0 minus 2x1. The derivative g with respect to x1 is going to be 0 minus 2x2 minus 0. And the derivative g with respect to x2 is going to be 10 minus 2x1 minus 2x2. Something to be aware of with this problem, if you happen to notice that you might make your life a little bit easier. These derivatives, or I should say these differential equations, are symmetric in the variables x1 and x2, meaning if you take this first equation and you interchange x1 and x2, you get the second equation. And when that's the case, you have the symmetry of your answers. If you look back at all of our equilibrium points, there's symmetry there. You get 0, 0, and you interchange x and y, you get 0, 0. You get 0, 10. If you interchange x and y, you get 10, 0. And you get 10 thirds, 10 thirds. And if you interchange that, you get 10 thirds, right? So when you have symmetry like this, every equilibrium point, its inverse is also an equilibrium point. Meaning you either get pairs like this or you get points that are on the line of y equals x. But what it also means is there's symmetry in your derivatives, right? This derivative being 10 minus 2x1 minus 2x2, I knew right from the get-go that this derivative was going to look the same as that because of the symmetry. So if you notice this symmetry thing, you can save yourself a little bit of mental energy. Let's go ahead and evaluate this Jacobian at all these points. Ugh, okay. So the Jacobian is 0, 0. Oh, that's going to be lovely. 10, 0, 0, 10. And everyone should be able to look at that matrix and without doing any other work, so for maybe a minute of thinking, tell me what kind of stability we have, or to classify the equilibrium. It's an unstable node because our eigenvalues are both positive 10. So unstable node. You might, I suppose if I was taking a test, I would probably write down lambda 1 equals lambda 2 equals 10 or something like that, and then write unstable node. But they wouldn't really do much more than that unless they really wanted me to do more. I plug in 10, 0. I'm going to get 10 minus 10. So that's going to, sorry, 10 minus 20 minus 0. So negative 10. I'm going to get a negative 20. I'm going to get a 0. And I'm going to get a 10 minus 20 again. So negative 10. So here we have a stable node because our eigenvalues are both negative numbers. And I think we're going to get the same thing at 0, 10, although let's be sure. But yeah, no, I'm definitely going to get, right? I'm going to get negative 10 again, 0 here, negative 20 here, negative 10 here, and see the result above. And then finally, the hard one. The one where there isn't a 0 somewhere. So if I plug in 10 thirds, I'm going to get, let's see. Well, it's actually kind of interesting. So if I plug in 10 thirds, I'm going to get 10 minus 20 thirds minus 20 thirds. I'm going to get minus 2 times 10 thirds is 20 thirds. I'm going to get minus 20 thirds. Get minus 20 thirds. Oh, sorry, that's not correct. It's 10 minus 20 thirds minus 20 thirds. Yeah, all right. So if I simplify this, it's going to be 30 thirds minus 40 thirds is minus 10 thirds, minus 20 thirds, minus 20 thirds, minus 10 thirds. Boo. I don't love it. Is there a way I can make my life easier? Maybe. Yeah. So here's what we could do. We should probably just do it let's just do it the long way. So if I was trying to find the eigenvalues, I would do the determinant of this matrix. Now, there's kind of a trick you can use here if you really want to know. So let's start writing this out. I'm going to get negative 10 thirds minus lambda times negative 10 thirds minus lambda minus negative 20 thirds times negative 20 thirds. I don't know if the trick is really worth mentioning. So there's a trick, but it only works if these are the same, which they are. So here's the quote unquote trick if you really want to see it. I could say, well, that's negative 10 thirds minus lambda squared. And then bring this over to the other side. It's going to be equal to negative 20 thirds, and negative 20 thirds is, I mean, I should just say it's 20 thirds squared, but it's 400 ninths. And then square root both sides. So I get negative 10/3 minus lambda equals plus or minus 20/3. And then I'm going to add lambda over there. And subtract and do this over there. It feels kind of like cheating. I'm not going to lie. I feel like I've cheated you of the experience of seeing me do it the long way. And because that only really works if you have specifically the same thing minus lambda times the same thing minus lambda. But let me ask you all, seeing this, let me ask you first. How do I want to phrase this? Are eigenvalues real or complex? Obviously real. I mean, there's no imaginary numbers here. Are they both negative, both positive, or one of each? One of each. So what do we have? Saddle. So I probably, in retrospect, could have just found the determinant of this matrix and seen that it was negative. So if we look back for just a quick second, this Jacobian, the determinant is equal to negative 10/3 times negative 10/3 minus something that's clearly going to be bigger. I've got 100/9 minus 400/9, which is definitely negative. I don't care. It's negative, which means you have a saddle. So especially if you luck out and get a determinant that's negative, it's always worth kind of at least asking yourself, could that determinant be negative? If it is, I could be done. That's what I would say about that. What time is it? 2:43. Okay. Let's see. I feel like there was something else I wanted to mention here. Unless you all have a question. Oh my gosh, my thumbs don't work anymore. Oh yeah, there's that one. Sure. So let's look at one more of these nonlinear ones, because I want to point out something. Let's say we have something like this. Dx dt is equal to negative 5x plus xy, and dy dt is equal to, sure, y minus 10xy. And we want to find all the usual stuff. We want to find and classify all the equilibria. All right, so again, we're setting each of these equal to 0. If I set this first one equal to 0, what should I do? Whenever you're doing this, if you can, you should factor. I'm going to factor out an x. Great, so I get two possibilities. I get either x equals 0 or I get y equals positive 5. And I want to be extra super clear here. 0, 5 is not an equilibrium. Because if you plug in 0 for x and 5 for y, sure, this equation is 0. This equation is not. If x is 0 and y is 5, you're going to get 5 minus 0, which is not 0. So I want to be extra super clear, right? You have to have something that makes this 0 and something that makes this 0. So we're going to take each of these different conditions, and then we're going to plug those into the other equation, b equal to 0. So my other equation is, I'm going to factor out a y. Y times 1 minus 10x equal to 0. So either if I have x equal to 0, well, then I have y times 1 equal to 0, which means y equals 0. Great. So that's one equilibrium. Or I have y equal to 5. Y equals 5. I have 5 times 1 minus 10x equal to 0. So what's x going to have to be? Well, 1 minus 10x is going to have to equal 0. 1 is going to equal 10x. X is going to equal 1/10. So I only get two equilibria. My equilibria are not surprisingly 0, 0. I mean, it's pretty obvious if you look at the original. Oh yeah, if you set x and y both equal to 0, you're going to get 0 plus 0, 0, 0 minus 0, 0. Usually, unless someone's, and you guys, I should actually back up. He hasn't said anything about non-homogeneous systems, has he? No, I didn't think so. I haven't seen it in his notes anywhere. So sometimes you have these weird systems where 0, 0 isn't an equilibrium. He hasn't talked about that. He's not going to ask you about it. Don't sweat it. But other people have in the past. 0, 0 is almost always an equilibrium. And then we also have the less lovely, but still wonderful, 1/10, 5. And those are the only two equilibria. I'm going to stress again, 1/10, 0, 5, not an equilibrium. 1/10 is 0, not an equilibrium. Those don't work for both equations at the same time. And if you're not sure about that, try plugging them in. Try plugging in x equal to 0 and y equal to 5 into this equation and this equation. One of them won't be 0. And do it for this one as well. One of them won't be 0. All right, now the usual thing, we're going to find the Jacobian. So it's going to be the derivative of the first equation with respect to first x, so -5 plus y, and then y, it's going to be just x. And then the derivative of this second equation with respect to first x, -10y, and then with respect to y, which is going to be 1 minus 10x. All right, let's see what we get. J of 0, 0 is going to be -5, 0, 0, 1. And what do we have? We have a saddle. At 0, 0. Right, our eigenvalues, 1 -5, 1 +1, opposite sign. And then plugging in the other point, which is 1/10, 5, we're going to get 0, 1/10. Let's see. I feel like I'm doing the math all wrong here. -10 times 5 is -50. 1 minus 1/10 times 10 is 0. Okay, and it doesn't look like it. Well, the trace is 0. What's even the trace is 0? One of two things, actually. So if the trace is 0 and you're above, you have a neutral spiral. If the trace is 0 and your determinant's negative, what do you have? Saddle, right? Determinant's negative is always saddle. Is my determinant negative? Not. It's positive. My determinant here is 0 minus 1/10 times -50, which is +5. My trace is 0. That means we have a neutral spiral, also called a center. Question? No, I used to think that too. So actually, let's go ahead and see it, just because I do think it's something you guys would want to see. So let me show you real quick. We got time. We got time. Where's my graphic stuff? Okay. So if we take this equation, which is dx dt equal to -5 times x plus x times y, and dy dt is y minus 10 times x times y. All right. And we might want to go a little bit bigger on our window here. Maybe I need to get my mouse over there. Is that a -5 there? Make it a -7. Sure. All right, let's take a look. That does not look very centery. Oh, so here's the thing. That's actually, so really good point. This is not going to look like a center everywhere around. Near your equilibria, it's going to have the behavior that you're talking about. So near 0, 0, it's going to be this kind of unstable saddle kind of deal. And then near our other equilibria, which is, oof, what was it again? It was 110, 5. Okay, so, oh boy. So this is not a great example of graphing a thing. But around here, no, it's not very good. Sorry, I'm not helping you out with this at all. So what's happening is, so we have an equilibrium there at 0, 0, and another equilibrium over here at 1/10, 5. And here we have a saddle, so things are kind of going in one direction, out the other direction. I like that. And over here we have a center, which means locally, if you're right there, you're just going to be kind of going in circles. You don't spiral out, you don't spiral in, you just spiral around and around and around. So, right, inward spiral or a stable spiral looks, like you're going inward. An outward or an unstable spiral kind of is the opposite thing, right? You're going outward, away from the origin. And then a neutral spiral is this kind of thing that just looks like a circle, where, right, if it was around the origin, you would literally go back and land at the same spot you started at. So this is a neutral spiral in a particular direction. It's not a point, but whatever initial condition you start at, let's say this is your initial condition here, you're going to exactly spiral back around to that same spot. And the reason why that's the case is because in the neutral spiral, the trace is 0, meaning there is no real part of your eigenvalue. So we actually look back at this equation for a second. And if I look back here, so we had our trace was 0, our determinant was 5. So we actually can see that the eigenvalues would have been the trace, which is 0, plus or minus the square root of 4 times, or minus 4 times the determinant, all over 2, which ends up being plus or minus negative, square root of negative 20 is going to be I root 5. You don't have any real part, meaning if you were to write your general solution, which I know is kind of a large thing to do, but if you're going to write your general solution, which is, your x of t, y of t, which is your c1 e to the lambda 1t plus times v1 plus your c2 e to the lambda 2t times v2. What's happening is you're having your c1 e to your lambda normally would be like an a plus or minus bi, right? Because it's complex. You have your a plus bi times t times v1 and your a minus bi times t times v2. And normally what happens is we see that, I'm just going to talk about this part for a second. This part here makes it either grow or shrink, right? If a is positive, this grows the value, right? It's going to get bigger and bigger and bigger as time goes on. And if a is negative, this shrinks the value. That's why we get instability when the real part's positive, because the values are getting larger and larger and larger. We get stability when the real part's negative, because the values get smaller and smaller and smaller. But when a is 0, when you don't have a real part, this is just 1. We don't have growth or shrinkage, but we do have this oscillation, right? The imaginary part of the eigenvalue is what gives you the spiralingness. And so if you just have spiralingness and you don't have growth or decay, you just get this infinite spiral that's going back on itself over and over and over again. That's why you have a center when the trace is 0 or the real part of the eigenvalue is 0. You don't, because it depends on where you start. So let me show you, because I can show you if I actually just, so let me come up with an example real quick of a matrix that definitely has an imaginary eigenvalue and no real part. That's easy. We can totally do that. So I want, let's say we have a 2 and a -2. That's going to make the trace 0. And I want the, sorry, you can't see what I'm writing. Let me close this down for just 1 sec. I promise you, it might be worth it. So my trace is 0. And I need my determinant to be big enough that this is going to be negative. Well, I just need my determinant to be positive, right? That's going to be negative. So I want, let's see, my determinant is going to be -4 minus, let's make it easy. I want to be positive though, not negative. Let's make it. Cool. So now my determinant is -4 minus -12, which is going to be positive. Okay, so this matrix should have imaginary eigenvalues, and it should have 0 real parts. The trace is 0, and the discriminant part here is definitely going to be negative, because you get 0 minus 4 times 8. So this should give us a center. Let's take a look and see. Let's hope that I got it right. So I'm going to have 2 times x plus 3 times y. I'm going to have -4 times x minus 2 times y. I'm going to pray it. Yeah. So look at that. So here, no matter where we start, we loop back on ourselves. But the diameter depends on what your initial condition is, right? So my initial condition, is say 0, 4. I have kind of a big loop. If my initial condition is like 1, 0, I have a small loop. But I'm not spiraling inward. I'm not spiraling outward. On the other hand, if I change it so that my trace ends up being just a little bit positive, assuming my determinant is still the same, I'm expecting now this to be an outward spiral. Oh, look, it is. So the trace being, or the real part being just a tiny bit positive, makes it spiral outwards. We have an unstable spiral. On the other hand, and right, no matter where you start, you spiral outwards. On the other hand, if we have a slightly negative trace, now it's spiraling inwards. So eigenvalue being complex, imaginary, means we get spirals. And the stability of the spiral completely depends on the real part, which is just the trace. So if the real part's positive, or if the trace is positive, you're spiraling outward. If the real part's negative, or if the trace is, negative, yeah. The real part's negative, or if the trace is negative, you're spiraling inward. And if you're in the rare case where the trace is 0, you have a neutral spiral. You're not spiraling outward or inward, you're just spiraling in the same single loop over and over and over again, forever and ever. All right, it is 3 o'clock. I should stop talking.